Yo, what's up guys? Welcome back to another video of Algebra 2. Sorry for being inactive for the past few weeks. I was grinding the APs. And today we'll be learning trigonometric expressions and equations. And if you're wondering what book I use to help you guys study, it's just this Let's Review Algebra 2 for the New York State Regents exams. These are pretty good. And so, well, let's start off. So this video is going to be a little different. Before I had little outlines and everything, but right now I'm just going to do examples and explain on the way. So, okay, so first off, we're finding the length of the legs of a right triangle with a unit hypotenuse. So let's say there is a right triangle. B, C, A. This is 40 degrees, and this is a length of 1. So what we have to do here is, well, actually, sine 40 right here. Sine 40 is that you can think of it as the length of the side opposite the 40-degree angle in a right triangle. So right here, sine 40 is this right here. Okay, and if you enter sine 40, it should equal 0.6428. So what this number means is that in a triangle of ABC with a hypotenuse of 1, side BC is approximately 0.6428 units long. Okay, and try this out for yourselves. If your calculator gets a different number, it may be that you have to switch your calculator to degree mode. So yeah. Okay, let's do some examples. So in the triangle right here, right triangle, 72 degrees if you can't read it, and the hypotenuse is 1. So what is the length of side BC? Okay, so the length of side BC, as we did before, it would be sine of this, sine 72, and that would be the opposite. So sine 72 equals around 0.9511. Once again, this means that this side, BC, is 0.9511 units long. Okay? And on the other hand, we have cosine. So cosine of an angle can be thought of as the length of the side adjacent to the angle. So for instance, in this triangle, BCA, with the hypotenuse length of 1 and 40 degrees, cosine of 40 will give you the length of this, CA. So cos 40 is around 0.7660. Once again, that means that this side is 0.7660 units long. Okay, and let's move on, I guess. And then next up, I'll teach you guys like a little acronym that my school uses. It's SOHCAHTOA. I'm pretty sure you guys heard of this before. And it just tells you exactly what, how everything works. So like sine, this basically means sine of whatever angle, say angle theta, equals opposite over hypotenuse. And that's basically what it means. Once again, cosine. Adjacent this time. Adjacent over hype. And then tan is opposite over adjacent. And that could be all like basically done with this little acronym. SOHCAHTOA. Okay, next up, we got how to locate points on the unit quarter circle. So a unit quarter circle is a part of a circle centered at 0, 0 with a radius of 1, and it's in the first quadrant. So essentially we'll be only seeing this part here. Okay, so let's say there's like a little little graph here. 0.2, 0.4, 0.6, 0.8, all the way to 1. Let's do that again. I'm just going to shorten it. And what the unit quarter circle looks like is just this. It's basically like a little. Alright. So the point of this is if a radius is drawn in this so that the angle between, oops, I should write it down. Angle between OP and OA is 27 degrees. It is possible to find the coordinates of the endpoint of the radius P by drawing the line segment PR perpendicular to the x-axis. So, let's see. This is pretty simple to understand. Endpoint P right here. Let's say this is a radius. It's not a straight line, but and it goes directly down to R. This is a right triangle right here. At this 27 degrees. And so, essentially, the point of this is that hypotenuse is 1, and the coordinates of point P are cosine 27 and sine 27. That's essentially what it is. So cosine of this, that's x, this is y. Alright? Let's try an example. So, let's say you have a unit quarter circle, angle AOP is 61 degrees. What are the coordinates of point P? You can draw it out, I guess, if you want. I'll draw it out for you guys. Once again, everything's 1, you know, and goes through point P, goes down to R, right angle, and this is O. What you have here again is a right triangle with 61 degrees. So point P is cosine 61 and sine 61. Those are the coordinates, okay? Moving on, we have locating points on a full unit circle this time. So even if angle AOP is greater than 90, the x-coordinate of point P will be the cosine of AOP, and the y-coordinate of point P will be sine of AOP. So if you don't get it, we'll just draw the graph. So the full unit circle, I'll draw it really briefly. Okay. And in the unit circle above, AOP is 160, so around right here. Right? And in this case, coordinates of point P is still cosine 160. Cosine 160 and sine 160. And this is about like negative 0.94 and 0.34. Okay. This way of thinking about sine and cosine with the unit circle is related to thinking about them in a right triangle. So let's say if you reflect segment OP over the y-axis to become OP prime, that acute angle of that prime would be 20 degrees. The acute angle you get when you reflect point P into quadrant 1 is known as the reference angle. Okay? So if angle AOP is greater than 360, point P wraps around and will be in the same location as some other point that is less than 360. For example, the point at 380 degrees is at the same location at the point 380 minus 360 equals 20. And so using this type of thinking, sine 380 is essentially the same as sine 20. Okay. And moving on, we have, one second, we have some trigonometry equations, and more specifically, we'll be learning how to approximate solutions to trig equations with the unit circle. So this unit circle explains why there are generally two answers to the trig equations. So let's draw it out. Let's draw a sample really quick. Okay, And there's a horizontal line at y equals 0.5. So right here, I didn't write it out. So the points on the circumference of a circle are 10 degrees apart from one another. As a horizontal line intersects the circle twice, there are 2 points on the circle that have a y-coordinate of 0.5, called P1 and P2. Okay? And let's label the rest. BOA. Let's just say this is BOA. Okay? You should note that angle BOP2 is the same measure as angle AOP1, because P2 is a reflection over the y-axis of P1. So angle AOP1 is a 30-degree angle, so sine 30 is 0.5. Angle AOP2 is a 150 angle, so sine 150 is also 0.5. Okay? So let's take, for instance, sine x equals negative 0.5. This also has a two-solution answer. So the line y equals negative 0.5 intersects the unit circle at P1 in quadrant 3 and P2 in quadrant 4. Just think about this in your head. These points correspond to the angles 210 degrees and 330 degrees. So to use the unit circle to approximate trig equations involving cosine, a vertical line is needed instead. Okay, so cosine is basically just this, but instead of like this horizontal line, it's vertical. It's like that. So let's try an example. Draw a quick unit circle. The question is cosine x equals 0.75. And then let's say you have all this labeled and everything's like graph. I'm just going to do it really quick. So let's say there's a line at 0.75, like that, vertical, because it's cosine, remember? So that means that angle AOP1 is approximately 40 degrees, while angle AOP2 is approximately 320. Okay? And in some cases, the unit circle and the vertical or horizontal line does not intersect the circle at all. So this means that the equation has no solution. And if the vertical or horizontal line is tangent to the circle, which means touching it at only one point, the trig equation only has one solution. Okay. And there's a different method to solving trig equations. It's more precise. You can just do it with a unit circle and a calculator. So let's do a little procedure, I guess. So example, sine x equals negative 0.94. This requires 4 steps. So step 1, you sketch a proper vertical or horizontal line on the unit circle. So for this example, let's say it's about, or it is actually negative 0.94. So this is my vertical line, because it's sine, remember, and this is the line. So step 2, you have to identify the quadrants for any points of intersection between the unit circle and the line from step 1. For this example, point P1 is in quadrant 3 and P2 is in quadrant 4. So if you didn't know, 1, 2, 3, 4. Okay, and step 3. Okay, so step 3, you have to determine the reference angle by taking the sine to the negative 1, the inverse sine, or the inverse cosine of the absolute value of the number after the equal sign. For this example, the reference angle is, once again, absolute value, so it's positive. I don't know why I wrote that. Which is around 70 degrees. That is your reference angle, okay? And step 4, depending on which quadrants the intersection points are in, use the following formulas. So quadrant 1, the solution is x equals just a reference angle. Quadrant 2, it's x equals 180 degrees minus the reference angle. I'll just name it RA. And quadrant 3, it is x equals 180 degrees plus reference angle, or RA. And quadrant 4 is 360, x equals 360 minus RA. Okay, so for this example, point P1 is in quadrant 3, P2 is in quadrant 4. The solutions are x equals 180 plus 70, which is 250, and x equals 360 minus 70, which is 290. Okay. Let's move on. Let's do a little example. So let's say, once again, you have a unit circle, or a quick one. And use the unit circle below and the calculator to find the two solutions to the nearest degree between 0 degrees and 360 degrees of the trig equation cosine x equals negative 0.57. Okay, so once again, repeat your procedure. Try this out for yourselves, and then we'll get started a little bit. Okay, so there is a vertical line in this case at negative 0.57, point P1, P2. So quadrant 2 and quadrant 3. And once again, reference angle, cosine, negative 1. Absolute value of this, 0.57, is around 55 degrees, okay? So the two solutions is 180 minus 55 equals 125, and 180 plus 55, which equals 235 degrees, okay? So moving on, we got radian measures. So just as length can be measured in different units, like feet or meters, angles could be also measured in different units. In addition to degrees, angles are often measured in a unit called radians. So one radian is approximately 57.3 degrees, I think. Yeah, 57.3 degrees, okay? And the circumference of a unit circle is 2 pi. That's 2 radians. So 2 radians, like that. Okay, let's draw a unit circle, help you better understand this. So in the unit circle, the edge of the unit circle is divided into 6 arcs. So, whoops, I didn't need to draw that, I just need a circle. 6 arcs, so let's say B, C, D, E, F, G, and A. And inside it's point O. As a note that this angle is smaller than the other ones. Okay. So the arcs are divided into. Wait, hold up. Okay, never mind. The 6 larger angles are each 1 radian. So 1, 2, 3, 4, 5, 6. That's 1 radian each. Since there are approximately 6.28 radians in a circle, the conversion factor is that 6.28 radians is approximately 360 degrees. So in 1 radian is 57.3 becomes 360 divided by 6.28 radians. Okay. So, and the exact number of radians in a circle is 2 pi. So the exact number of degrees in 1 radian is 360 over 2 pi, which is 180 over pi. And a quick little tip, to convert radian measures to degrees, multiply the number of radians by 180 over pi. So multiply, to convert radian to degrees, multiply this. And if you want to do the opposite way around, you just switch it. Okay. And let's try out an example of converting. So convert 3.49 radians to degrees, rounded to the nearest degree. So try it out. So basically, it's 180 over pi, which equals around 200, I would say. Let me see. Yeah, 200. Okay, and let's try one more, just in case. 2 pi over 3 radians to degrees. Give an exact answer. So exact in this case is a little different. Multiply over 3 pi equals 120 degrees. And you want to keep the pi's if you have them, right? Because it says exact, remember. This is just a little bit rounded, you know? Okay, and let's try converting degrees to radians. So practice converting 50 degrees to radians, rounding to the nearest hundredth of a radian. So solution, 50 degrees times pi over 180. Simple. And that's around 0.87 radians. Okay, and exact, 135 to radians. Exact. It's 135 times pi over 180. And here is an example of keeping the pi, which simplifies down to 3 pi over 4 radians. Right? So, yeah. If you guys want to memorize some common radian to degree conversions, it wouldn't really matter, but it could help. So 360 degrees is 2 pi. 180 pi, 90 pi over 2, 60 pi over 3, 45 pi over 4, and 30 pi over 6, where this side is radians, this side is degrees. Okay, and moving on, we'll be learning the graphs of the sine and cosine functions. So graphs of the sine and cosine functions, each point on the unit circle conveys 3 pieces of information: the angle AOP, the cosine of AOP, the coordinate of P, and the sine of P. So if you want to see a graph, like right here. So once again, it will reveal 3 pieces of information, graphs like these: the angle AOP, the cosine of AOP, and the sine of AOP. Basically, the last 2 parts are just the x coordinate of P and the y coordinate of P. Okay. So moving on. The information from the unit circle can be put into a table. So point A, B, C, D, E, F, G, H, I. So essentially, I'm not going to write them out because that's too much work. The angles, what you want to note is angles, cosine x and sine x. This is basically x coordinate, this is basically y coordinates. And once you have all of those, you graph them. Graph the 9 points with the angle measure as the x coordinate and the sine x as the y. So the final graph would be like something like this, like that. Okay? Where these points are like 0, let's say 90, 180, 270, and 360. Okay? And these graphs can also be created on a graphing calculator. So if you have the TI-84, essentially, you have to do, press Y equals, enter sine x, and then just press zoom 7, and you should get a graph that looks like this. Okay, moving on, we'll be learning the amplitude of sine and cosine graphs. So in a function like gx equals 3 sine x, the number right here is known as the amplitude. Okay, and this coefficient transforms the graph with a vertical stretch. So what this does compared to just a standard function is that the highest point on the graph is now 90 degrees 3 instead of 90 degrees and 1, and the bottom is 270 negative 3 instead of 270 negative 1. And if the coefficient is negative, there is also a reflection of the curve over the x-axis, so it would be just reverse, like yeah, like that, really briefly. Okay, so we'll be moving on to vertical translations of sine and cosine graphs. So I think you'll get this pretty easily. I'll just skim this over once again. Sine x plus 2, this plus 2 means that it's shifted 2 units up. And once again, minus 2 shifted 2 units down. Okay? And there's also something called the frequency of sine and cosine graphs. So something like sine 2x. Like this thing. Okay? So if it's in the parentheses as such, the graph of the function is like the graph of the standard function, sine x, let's say, but with the horizontal squeeze by a factor of 2. Okay? So essentially, the frequency is the number of complete waves that fit inside a 360-degree interval. Okay? So like if the standard graph is like, bam, it's not accurate, but I'll try to make it bad. And so the shifted one would be like that, kinda. Okay? Moving on, we got something called the period of sine and cosine graphs. So the period is the number of degrees or radians needed for the curve to complete one cycle. This period can be symbolized by the formula P equals 360 over B or 2 pi over B. One's for degrees, one's for radians. Okay? So, and by the way, these B is frequency. It just stands for frequency. So you plug in the frequency. Easy. Okay? And once again, you can combine more than one transformation, like -3 sine 2x plus 1, and essentially the things that we just learned before. Okay? And you can also find the equation of a function from a given graph. So let's say there's a question, it's just a graph, and it just asks you to find the equation. That's easy. You have to make 5 decisions in order to find this equation. You have to ask yourself, is it sine or cosine? And then you have to ask yourself, what is the vertical shift? And then you ask yourself, what is the amplitude? Then what is the frequency? Then is the coefficient A negative or positive? Okay? So the way you know, I don't think I told you yet, the way you know if it's sine or cosine, cosine does not start at the origin. Like cosine would be like that or something, or like that. It does not start at the origin. It starts at a higher point or a lower point. And the sine graph, it just starts at the origin, like that. Okay. The rest is pretty simple to understand. And so we can also graphically solve trig equations. So you can use this. You can use the intersect feature of the graphing calculator. The graphing method is very quick and accurate, as long as the question does not specify that only a algebraic solution will be accepted. Okay. So what you have to do, solve something like sine x. You just plug this into y1 and y2, and you just set it to intersect. You just trace the intersect and then write them down as the solutions. Okay? It's pretty simple. And there's also real world scenarios for trig functions. So commonly the models would be based on spinning circles, bouncing springs, and weather patterns. So like most things that go up and then down and then up and then down, like repeatedly, can be modeled with a trig function involving sine or cosine. Okay? So let's say the most common one is a Ferris wheel problem. So let's say there's a Ferris wheel. I'm just gonna draw it like really badly. Or whatever. There is a radius of 10 feet, let's say. And the bottom of the Ferris wheel is 3 feet from the ground. Okay? Draw like that. So when Evelyn gets on the Ferris wheel, she's exactly 3 feet above the ground. Then 50 seconds after starting, she will be 23 feet above the ground at the peak of the Ferris wheel. Then 100 seconds after starting, she will be back to her starting position exactly 3 feet above the ground. Okay? So the graph of this essentially would look like this. I'm not going to write out the units, but I'll just write out the points that are important. So 0, 3, her start, her end, 103, and her peak, 50, 23. Okay? So using the methods from earlier, the equation would be -10 cosine pi over 50 x plus 13. Okay? It's pretty simple. So with this equation, you can answer two different types of other equations. So how high above the ground will Evelyn be after a certain number of seconds? And you can also answer the question, after how many seconds will Evelyn be a certain number of feet above the ground? Okay? So you just plug in whichever which, and whatever the question asks you, you just do. Okay? And you could also do this with temperature. If they give you like a table that has the temperature in New York over the course of 2 years, you can find the function for that, and then from there you can solve what is the temperature in a certain time, and at what 2 times is the temperature approximately what degree, you know? So it's pretty simple to understand. And then next we have a trigonometry identities. So a trig identity is an equation in which the left side and the right side both contain trig expressions. So complicated trig expressions can be simplified by replacing parts of it with equivalent expressions and simplifying the new expression. Okay. And a little note: sine x, like this, squared, can be rewritten sine squared x. So this is just to make it clear that it's not confused with this. This is wrong right here. This is wrong. This is right for this. And same thing with cosine. Okay? So there are 5 main trig identities. So 1, sine squared x plus cosine squared x. 1. There's sine squared x. If you just manipulate the one above. And there's with another manipulation. Okay, there's 2 tan x equals sine cosine x. 3 cosecant x is 1 over sine x. And 4 secant x equals 1 over cosine x. 5 cotangent is 1 over tan x, like that. Okay, these trig identities can be used to identify trig expressions that are equivalent to other trig expressions. Okay, so essentially, you just convert, basically. It's pretty simple. If you see any of these trig identities, you just apply them. It's pretty easy. And if you want to combine fractions in the trig identity problems, you got to make sure, like common fraction combinations, you have to have a common denominator. So for example, you cannot, let's say like we're showing that sine x times tan x plus cosine x equals secant x. So we're just write it out, solve it out. Convert your trig identities. And then sine squared x, sorry, over 1. So here, the common denominator for the two fractions is cosine x. and then you can just solve it. Essentially we'll be left with this, and you can convert it to secant x. Okay, so they're pretty easy to understand, and let's move on. Oh, no, that's done. Okay, never mind. And then in the next video, stay tuned. I think I'll be releasing it either today or tomorrow. We'll be learning how to do system of equations, and it's pretty short, I guess. A couple of a few pages. Yeah, it's pretty easy. All right. So quick shout out to the homies, Dan Ra, Christine, Danny, Jana, and Mohammed. They helped me a lot. And I'll see you in the next video. Stay safe, guys.